just when you thought your favorite topic was gone, it is back. Chapter 11, Part 3, Stoichiometry of Gases. How exciting. I know, it's what you've been waiting for. The good news is it's not much different from what it was before. So, for gaseous reactants and products, remember that we have coefficients in our balanced equation. The coefficients indicate the mole ratio and therefore the volume ratio. So those are interchangeable. So we can actually compare volumes of gases if the gaseous volumes are measured the same way at the same temperature and pressure. So we're kind of taking gas laws plus stoichiometry and kind of rolling it together. So there are a few different types of problems, just like the normal stoichiometry. Like I said, the good thing is this should look familiar. So volume to volume stoichiometry, I would compare to mole to mole. Okay, one step, you start with a known volume of substance in liters given to you in the problem, and then you multiply by the volume ratio, the unknown over the known. Those numbers come from your coefficients in your balanced equation, and your final answer is your unknown volume in liters. So the only thing you need to know for this is you have to be in liters, and your equation has to be balanced. So let's try a problem. As I keep saying, if you actually try these problems yourself, you're going to get better at them quicker. If you just sit there and watch me do it or fast forward, you're going to be struggling with the worksheet. And if you get stuck on the worksheets, come back to these problems. They're worked out for you. They're very similar. Okay, so we have a chemical equation. Notice I already balanced it for you. You're welcome. Okay, so the question is, what will be the volume in liters of oxygen required to complete a combustion reaction using 0.35 liters of C3H8? So let me get my highlighter. So we have that much of C3H8, which is right here. And the question is volume of oxygen, which is right there. So if you want to write underneath your problem, 0.350 liters and question mark liters. So as I said, this is very similar to mole stoichiometry. So once again, units and labels are important. I start out with my known number, 0.35 liters of C3H8. That came from the problem. Okay, one conversion, and that is my volume ratio, which is equivalent to the mole ratio, my unknown over my known. So my unknown is oxygen, so I'm going to use the unknown coefficient of 5 on the top. And my known is C3H8. I'm going to use that coefficient on the bottom, which is 1. My units are not moles anymore, but they are liters. So like I said, very similar. So C3H8 goes on the bottom. It had the coefficient of 1, and O2 goes on the top. And that's it. So in your calculator, you would do 0.35 times 5 divided by 1. Okay, and I got an answer of 1.75 liters of O2. My units and labels cancel out. I'm left with liters of oxygen, and that was the question. What will the volume in liters of oxygen be? Okay, so very, very similar to what you've been doing before. Volume to volume stoichiometry, similar to mole stoichiometry. Okay, I'm actually not going to work this problem out for you. I want you to try it yourself. Okay, here is your given number, and here is your unknown. So try this yourself. Pause the video, and then I'm just going to throw the answer up here. So hope you actually tried the problem. I'm starting with my known amount of C3H8. I'm multiplying by the volume ratio, which comes from the coefficients in my balanced equation. And my answer is 1.05 liters of carbon dioxide. So if you didn't get that, look at my work, ask questions if you need to. All right, try this one. Like I said, Try it yourself. Go back to the previous problems and I'll throw the answer up here. So hopefully you balanced it correctly. 2, 1, 2. I have 4 hydrogen on each side, 2 oxygen on each side. So I'm starting with my known amount of oxygen gas, and I am simply multiplying by the volume ratio, which comes from the coefficients of the balanced equation. Unfortunately, if you don't balance it correctly, obviously you're not going to get the right answer. So make sure you're balancing correctly. If you need a refresher on that, let me know. So I take 4.55 liters from the problem times 2, which is my coefficient of my unknown, divided by 1, which is my coefficient of my known. And I get 9.1 liters of H2. Hopefully you did too, or close to that. All right, next up, volume to mass, stoichiometry of gases. There's 2 steps here. Okay, you first have to convert from grams to moles using the ideal gas law equation, solving for N. You have to be in moles to start stoichiometry. Some of you were forgetting that last section. And then P has to be in atmospheres, V has to be in liters, T has to be in Kelvin. Those will be given to you, but you may have to convert. And then you simply do mole to mass stoichiometry, if you will. So volume in liters to mass in grams is what we're trying to do. So here is the arrow setup if you like that. So I'm going to have a known amount in moles given to me in the problems, or like I said, of course, I'm going to complicate it for you. You may have to convert it to moles to start. You take that number times your mole ratio, unknown over known. That comes with the balanced equation coefficients. Then you multiply by the molar mass of the unknown. And then you get your unknown substance in grams. So that arrow step is pretty much the same as stoichiometry that you did before. Now you just have to go from volume to moles first. Okay, so try this problem. I will tell you it's already balanced. It's 1, 1, 1. So how many grams of calcium carbonate, which is CaCO3, must be decomposed, which means to break down, to produce 5 liters of carbon dioxide gas at standard pressure and temperature? Okay, so our unknown is going to be calcium carbonate, and our known is 5 liters of carbon dioxide. Okay, so the first step is to solve for N. So step 1, I'm going to use the equation N equals PV over RT. So in the problem, I have this, STP, standard temperature, standard pressure. That's what it stands for. Okay, so standard pressure is 1 atm. V is right here, 5. Standard temperature is 273 Kelvin. And R is the same constant we've been using. Okay, so if we plug in our numbers, P of 1 atm, you have to be an atm to start, times V, 5 liters, divided by R, times T, which is 273 Kelvin. Okay, some of you are having the right work, but you're getting the wrong answer. If you get the wrong answer here, it's going to mess up the next step. So in your calculator, put a parenthesis around the top. So parenthesis, 1 times 5 parenthesis. Then hit the division button and put a parenthesis. 0.0821 times 273 parenthesis, and then click equal. I promise it will help you. It will work every time. Okay, so doing this math, 1 times 5 divided by the entire bottom, I get 0. I'm not going to overround. This is another place some of you are going crazy. I'm going to go 2231 moles of carbon dioxide. So I just went from liters to moles. That's step 1. Okay. Now I have to go moles to grams. So now I'm going to use mole to mass stoichiometry. So 0.2231. First step is mole ratio, where I have a coefficient of 1 here, and I have a coefficient of 1 here, so it's 1 over 1. Unknown on top, known on the bottom. Okay? And then I have to multiply by the molar mass of CaCO3. So I've got 1 Ca, which is about 40. I've got 1 carbon, which is about 12. And I've got 3 oxygen, and about 16. So add those all together, you should get about 100 grams. Also, some of you are getting this part wrong just because of simple math errors. And then 1 mole of unknown on the bottom. So step 2 is just mole to mass stoichiometry like you've been doing forever. So 0.2231 or about that, whatever you got rounded, times 1, divided by 1, times 100, divided by 1, and I get 22.31 grams of calcium carbonate. I went from liters of carbon dioxide to grams of calcium carbonate, volume to mass stoichiometry. Okay, try this one. It is already balanced again. What mass in sulfur, S, must be used to produce 12.61 liters of gaseous sulfur dioxide, given standard temperature and pressure? Try it out. All right, so it's already balanced. So step 1 is to find moles given pressure, volume, and temperature. So standard pressure 1, standard temperature 273 Kelvin, volume V within the problem, and R is a constant. So I got about 0.5626 moles of sulfur dioxide. I went from liters of sulfur dioxide to moles. If you round to 0.56, okay, I guess. Try not to round it to 0.6 only. Don't overround, okay? It's going to mess up your decimals at the end. All right, and then step 2, I took my mole number that I solved for, and now I'm doing mole to mass stoichiometry. So I multiply by the mole ratio, 1 over 1, because each coefficient was just 1, my unknown S over my known. And then I multiply by the molar mass of S. S is not diatomic, so S is 32 grams. So I took 0.5626 times 1, divided by 1, times 32, divided by 1, and I get 18 grams of sulfur. I went from liters of sulfur dioxide to grams of sulfur, volume to mass stoichiometry. All right, last one. Try this out. Actually try it yourself, and then I'll throw the answer up here. All right, so see what you got. So I have about 0.1533 moles to start. Like I said, I didn't want to overround it from my initial work. Times 2 over 1, that comes from my coefficient of my unknown over my known, times the molar mass of H2O, so oxygen is 16, hydrogen is 1, and there's 2 of them, so 16 plus 1 plus 1 is about 18. So I get a mass of about 5.53 grams of water, or close to that. So once again, I went from liters of oxygen gas to mass in grams of water. And if you have questions, if you didn't get that right, come to office hours, chat me. So our last type of stoichiometry is mass to volume. It's kind of just flip-flopped, okay? Same style of what you just did, just a slightly backwards, if you will. So once again, 2 steps. You're first going to do mass to mole stoichiometry. So you're going to take your mass in grams divided by the molar mass of the known times the mole ratio. You're then going to get moles of unknown. And then you're going to use N, which you just solved for, in this calculation using the ideal gas law. nRT divided by P will give you volume in liters. Okay? And you have to be in moles to do step 2. So that's why you have to do step 1. All right, let's try a couple problems, and I think you'll be good to go. If not, you can always come to office hours. All right, how many liters of gaseous carbon monoxide, so that's going to be my unknown, liters, can be produced, I'm going to skip the information right now, can be produced from burning 65.5 grams of carbon. So I've already balanced it for you. The other important information is temperature and pressure. Notice I'm not in standard anymore. And like I said, you need to know that mass to start. All right, so step 1 is mass to mole stoich. You should be experts at this by now. So 65.5 grams of carbon. Carbon's not diatomic. 1 on the top. The molar mass of carbon on the bottom, which is just 12 or about 12. Step 1, or part 1 of this, I guess. And then we're going to multiply by the mole ratio, my unknown coefficient, over my known. So 65.5 times 1 divided by 12 times 2 divided by 2. And let me find my notes. I get 544. Whoops, that's wrong. Sorry, looking at the wrong stuff. I get 5.46 moles carbon dioxide. So I went from grams of carbon to moles of carbon dioxide. That's a point of stoichiometry, changing from one unit of one substance to a unit of a different substance. All right, step 2, I'm going to use the equation V equals nRT over P. So N, I just solved for right here. R is our constant. T is given to us in the problem. 27 degrees Celsius converts to 300 Kelvin. And pressure is given to us in the problem as well. So I take 5.46 times 0.821 times 300, all divided by 0.247. And my answer is about 544.45 liters of carbon dioxide. So I went from grams mass of carbon to liters volume of carbon dioxide. All right, try another one. Try this one. Balance it, try it out. I'll throw the answer up there. All right, hopefully you balanced it correctly. 212, you need that correct to get started. All right, so for step 1, stoichiometry, mass to mole, I take my given amount of grams of sodium. I divide by the atomic or molar mass of sodium, which is 23, and then I multiply by my mole ratio, which came from my coefficients, my unknown of chlorine over my known. And I got about 0.2261 moles of chlorine. Step 2, once again, I use V equals nRT over P. I'm solving for V. So N is right here. I just solved for it. That's why it's important that, whoops, sorry guys. That's why it's important you correctly solve for the first step. Times R, a constant, times T, which is 38 degrees Celsius. Convert that to Kelvin and you get 311. All divided by pressure in atmosphere, which it already is for me. If you do that math, you get volume to be about 3.54 liters of chlorine. I went from grams of sodium to liters of chlorine, mass to volume. All right, try one more. Already balanced for you. Try this one. I'll throw the answer up there for you. If you need help or you didn't get it, you know what to do. Contact me via chat or come to office hours. So hopefully you're ready to check. I got my final answer of 291.83 liters of hydrogen gas. If you didn't get that, first off, make sure your setup's correct, both parts. If your setup's correct, check your numbers. Did you get the correct molar mass for, whoops, this is W03. Did you get the correct mole ratio? And did you get something similar to my mole number? If that's all right, go down here. Is this setup correct? Did you convert Kelvin correctly? If that's all correct, throw it back in your calculator. It's probably just a calculator error. Okay, so that is the third part of the chapter, gas stoichiometry. We have volume to volume stoichiometry, volume to mass stoichiometry, and mass to volume stoichiometry. You're going to have a worksheet on each of these. So if you have any type of question throughout, please come to office hours. I do not have hardly anybody showing up. I can't help you if you don't ask for help.